Okay, so this is the title. It's a work in collaboration with these four people, Lorenzo, Franco, and Alessandro. They are all here, so you can talk to them if necessary. A good part of the talk will be dedicated to introduce a lowest order element, which is the extension, as you will see, to polyhedral decomposition of the lowest order net-elec first kind. So I will introduce the Vem spaces with the corresponding degrees of freedom. I will write the discrete problem and give you error estimates, plus numerical results. Then, in the remaining, the very last, in the last part of the talk, I will give you hints on a whole family of elements, similar but different to that one, which is the extension to polytopic decomposition of net-elec second kind, not first. So the problem is the classical magnetostatic problem. J is the current density given, divergence free. Mu is the permittivity, and we are looking for the magnetic field H in H curl and the magnetic induction B in H div, verifying these two equations. It's gone already. Curl H equals J, the div B equals 0, and this is the relation between B and H. So there are many variational formulations associated to this problem, and among them we chose this one due to Kikuchi, introduced in the 89, where there are two unknowns, the magnetic field H and a pressure, a scalar function, which is introduced as a Lagrange multiplier to impose the divergence-free the divergence-free condition on B. So here again the same. For being a mixed formulation, we need these two conditions for having existence and uniqueness, ellipticity on the kernel, and in subconditions. And these two necessary and sufficient conditions are guaranteed hold true because this sequence is known to be exact. I think I wrote it, but I did not underline that omega is simply connected. So this is why this sequence is exact. So the problem has a unique solution, HP, with P identically 0, and H verifying curl H equals J and divergence B equals 0. So what do we want to do now? Well, first of all, we decompose our domain into a polyhedra P, and we need to define finite dimensional spaces, a subspace of H10 for approximating the pressure. This will be what I call V node, nodal space. An approximation of H curl, where we look for H, edge space, a V face, so a space for the approximation of B, which is the phase element, subspace of H div, and then subspace of L2. And we want to have this sequence, to construct this sequence in such a way that they form an exact sequence like their continuous counterpart. Plus, we need also, they have good approximation properties because we are, of course, approximating. So I'm going now to do this. These spaces will be defined element-wise, as usual, and then glued together as in the classical finite element procedure. And first, I will begin by defining the traces of these spaces on the faces of each polyhedra. So I'm going to treat first virtual spaces on polygons, on faces, okay? The nodal space on a face, on a generic face, that's very easy, is probably the first virtual space introduced for the Laplace, is made of functions which are continuous on the face with polynomials of degree 1 on each edge and harmonic inside. The degrees of freedom are very simple, the values at the vertices of the face. It is very easy to check unisolvents of these degrees of freedom, which are classical, and what is important is that when we glue together the spaces to create the global space, the choice of these degrees of freedom will imply global continuity. We want to be in H1, okay. Now, so far, so good. But then, what do we know about the functions inside here? Not much. We know that we know them perfectly on the boundary because they are P1 on each edge, but inside we know nothing. We know that they are harmonic, but if we want to know them, we should solve a harmonic problem, and we don't want to do that, of course. We also know that the space of polynomials of degree 1 is included there, and this is good for the approximation, which will be of order 1, okay? So let us see what we can compute on these functions. Well, we can compute the average of the gradient, but nothing more. This we can compute. I don't know why that line over there. Integration by part produce an integral only on the boundary, and this we can compute because on the boundary Q is piecewise linear. But simple quantities like the average of Q inside are not computable from these degrees of freedom. Then we observe that the average of Q can be written in this way. Divergence of what? This is x minus the coordinate of the barycenter. We integrate by parts. On the boundary, we can compute this because Q are known on the boundary, but this we cannot compute. We can compute only the average of the gradient, not gradient against something. Then we make the observation that I told you that polynomials of degree 1 are inside, and for them, this integral is 0. This one. The integral of grad Q is constant, and xf has integral 0. So we slightly modify the definition of our nodal space. This is why I called it V tilde and not just V node, by imposing this condition on all the functions inside, not only to the polynomials of degree 1. So the final nodal space will be made of functions continuous, P1 on each edge, and then verifying this condition, but of course to have the same dimension, not to change the dimension of the space, the functions will not be harmonic anymore, but the Laplace will be constant. The degrees of freedom are still the same, values at the vertices, polynomials of degree 1 are still inside, and again, checking unisolvents of the degrees of freedom is very easy. And if our face, our polygon becomes a triangle, these are nothing but classical linear conforming finite elements. So this for the nodal space. Yeah. And to conclude, now we can compute the average of all the functions inside there. And this will be useful, for instance, if we need to compute projection onto constant. Now the edge space, we proceed more or less in the same way. We begin by this definition. Our edge space is made of vectors which have tangential component constant on each edge, rot constant, and zero divergence. Similar to the rotated Rabiar-Thomas, so Nedelec first kind. The degrees of freedom are the values of the tangential component on each edge, and this will ensure global continuity when we glue the spaces together. And on these functions, we know perfectly the tangential component. We know that the constant, the vector with constant component are included there because they verify that, but also Nedelec first kind are included. For those of you less familiar with mixed finite elements, Nedelec first kind is the space generated by these three vectors, the two constant and then the vector y minus x. And it is easy to check that for this kind of elements, this integral is 0. They verify integral of v against xf equal 0. So we proceed like I did before. We impose this condition on all the functions of our space, not only to the Nedelec included there. So we modify, we add this condition, and of course we increase the degree of the divergence will not be 0 anymore, will be constant. The degrees of freedom are the same, and Nedelec first kind is included. And I stress that if the polygon becomes a triangle, this is the space of Nedelec lowest order, Nedelec first kind coincide. What can we compute? Well, we can compute for functions in here, just knowing the constant tangential component on the edges, we can compute integrals against polynomials of degree vector, which are polynomials of degree 1. This is important because this will allow to compute the projection onto linear polynomials. Indeed, this is the simple proof. By decomposition of polynomial, any polynomial of degree 1 can be decomposed in this way. Rho P2 plus a constant time xf. Then we replace this expression here, integrate by parts. This first is known, is computable because the rotation is, the rot is constant, and knowing the tangential component of the boundary, we know the rot. So this is the integral of a polynomial of degree 2. The second is also computable because v of t is constant. And this one is 0, okay, because it's imposed. Okay, so a summary. We can prove, I'm not going to prove it here, that this sequence, V node, V edge, P0, is exact. Okay. And here is a summary of the definition with different color. V node is there, and with its degrees of freedom, values at the vertices. And the edge is here, and I use different color to show you what goes into what. So if you take the gradient of a nodal, you see that since a Q is linear on each edge, the vector V equal grad Q will have tangential component constant. So the blue goes into the blue and the green goes into the green. This is not a proof, but just show you that if you take the gradient of the nodal, for sure you go into the kernel of the rot. Okay. In reality, it coincides. Now, finally, let me go to 3D. Now we have a polyhedron, and we have to define first, like I did before, space for the scalar function. That's very easy. Will be made of functions which are continuous in P. The trace on each face will be belonging to the node of the face, the space that I defined before, and harmonic inside. The degrees of freedom are simply the values at the vertices of the polyhedron. And then the global space constructed starting from here, as I said before, will be a subspace of H1 due to the continuity. Then the space, edge space, which has to be a subspace of H curl. Now, the definition is complicated, but the degrees of freedom are not. Indeed, the definition is that one. We have vectors with tangential component on each face belonging to the edge space, to two-dimensional edge space. And then tangential component constant on each edge, curl constant, divergence 0, plus this funny condition which is needed for proving unisolvence and other things. So the degrees of freedom are simply, as before, as for the two-dimensional case, the values of the constant value of the tangential component on each edge. And it's easy to verify, despite this complicated definition, that the vectors with constant component are included there, not only, but also Nedelec, lowest order Nedelec first kind. The expression is a constant vector plus this vector product. How is it in English? Huh? No, this in English. Wedge. Yeah, ma il prodotto vettore. Wedge product. Okay. Well, that one. So it's easy to verify that vectors of this kind, Nedelec first kind, verify everything, so it's included. And this is very important. When this polyhedron is a tetrahedron, we have exactly Nedelec first kind. So this edge space is the extension to polyhedra of Nedelec first kind element. What can we compute? We can compute the projection of an edge element onto constant. Nothing more, but that's enough. And this is the proof, because any polynomial of degree vector with 3 constant component can be written as the curl of x wedge and constant, a constant vector. Then the definition, by the definition of projection, this is the first step. Then we replace, this is a bit elaborated, we replace the expression of P0 there, integrate by parts. This is 0, this integral, because it's imposed in the definition of the space, plus the boundary term that we rewrite in green there, and then the integral on the boundary is written as the sum of integral on the faces, and on the faces, I told you before, then we know how to compute integrals of edge 2D against the polynomials of degree 1. So this one is also computable. To compute it probably on the code is not immediate, but Franco Dassi did it, so you can ask him. And now here we also need a space for the approximation of HDiv, so a phase space. And this is the definition, constant normal component constant on each phase, curl and divergence constant, plus the third condition there. which is needed for the exactness of the sequence. And here, what do we have? Well, you can check immediately that constant vectors are included there. Not only that, also Ravière-Thomas, lowest order Ravière-Thomas elements are included there. I remind you that the expression of Ravière-Thomas of order 0, lowest order, is that one. So if you replace that expression into the definition of the spaces, you see that everything is verified. The degrees of freedom are simply the constant values of the normal component on each face, and this will ensure that the global space will be a subspace of H div. Also, if this polyhedron becomes a tetrahedra, we have exactly lowest order Ravière-Thomas. My God. So the global spaces, I'm not gonna repeat. For proving error estimate and everything that we need this condition, the red one, mu constant, piecewise constant on each polyhedra. Then the global spaces are constructed gluing together the local spaces, and we proved that this sequence is exact, okay? So we are done, apparently. The sequence is exact, so we can write the discrete problem, and we have existence and uniqueness. This is precisely what we would like to write, okay? Exactly like the continuous version, the continuous variational formulation that we chose. But we cannot. We cannot because here the first integral is a scalar product in L2 between two phase elements. Curl H, the curl of an edge is a face. And we know nothing inside. We only know the normal component on each face. The second integral is an L2 scalar product between the gradient of a nodal, which is an edge, against an edge. But we don't know them inside. So we have to approximate this L2 scalar product in a suitable way. So this is what we will write: scalar product between phase element, scalar product between edge, and we need to construct them. And then we also need to define, but that's easy, a suitable, say, interpolant of the current, which is a phase element. I will show you how to construct, how we did construct the edge scalar product, and then the phase is the same. So I told you that for an edge element, we can project onto constant. So we use it. We start by defining on each element P the scalar product as the L2 scalar product between the two constant projection. But this is not enough. This will give us consistency, but not stability. So as usual in virtual element, we have to add something that ensures stability. In general, a symmetric and positive definite bilinear form that scales like the L2 scalar product. For instance, this is the most commonly used, the sum of the degrees of freedom properly scaled. And the phase scalar product is done in the same way. Again, L2 scalar product between projection onto constant plus stabilization. Now, the consistency is very easy to verify with this. This is the first line is the definition of our edge scalar product. The second part goes away if one of the two entries is a constant, as P0. So we are left with the first integral, and then by definition of projection, we obtain that if one of the two entries is the polynomial of degree 0, then our edge scalar product is exactly the L2 scalar product. So this is consistency onto constants. And then stability, under suitable mesh assumption that I will give you in a second, this stability form scales like the L2 scalar product, so our edge scalar product is equivalent to the L2 scalar product. and we are happy, we can write our discrete problem where Ji is defined, is the standard Doph interpolant into V phase. So we can prove that the problem has a unique solution thanks to the exactness property of the sequence, and the scalar solution pH is identically 0. Error estimate, we proved error estimate in this norm here with mu inside, and these are the assumptions on the mesh. Essentially star-shaped, uniformly star-shaped with respect to a ball big enough. Same for the faces, and we don't want too small edges, okay? Under this hypothesis, we have this estimate, which is precisely what we expect with the low-order elements. Numerical results. First is the domain is a truncated octahedron, and the exact solution that we chose was that one. Second problem on a cube with exact solution given by the curl of this function here. These are examples. I have to run. I have 45 minutes, right? No. These are examples of the mesh that were used for the octahedron, from the more structured to the less one, to the random one. And here we computed again. When we compute the error, we would like to compute h minus h sub h, but we don't know h sub h inside, so we compute the error between h and the projection of the discrete solution onto constants, and these are the slope for the different meshes from structured to random in L2 for the first problem, and for the second problem. So we see that everything goes as expected, and the scalar pH vanishes up to machine precision. This is a more realistic problem, but it's still a benchmark problem with known solution. So we have a a conductor inside, two conductors separated by a magnetic material. The current is constant in the two conductors. The permittivity is constant in the two conductors, and 10 to the power 4 in the magnetic material. These are examples of two meshes used, starting from from a two-dimensional decomposition into triangle and then extruded that one into two-dimensional polygons, extruded to polyhedra, and again we have the slopes, order 1 in slope in L2. Now, yes, I still have a little time to show you, give you hints on a family of Nedelec second kind. So now the degree is K. This will be our order of precision. We have, I will do like I did before. First on the faces, so two-dimensional spaces, then in the polyhedra. So on each face, the edge space, we need to define an edge space. This will be made of functions, vectors, which have tangential component of degree k, divergence of degree k, and rot of degree k minus 1. And the degrees of freedom will be, well, on the boundary as many as the moment of the tangential component to individuate the tangential component, then This kind of moments inside, these are associated to the divergence, and this third one. Well, it's quite easy to prove unisolvents, and what I want to communicate, the idea, not any proof, is that we have a serendipity version. And serendipity version allows us to eliminate the internal, maybe not all of them, but these degrees of freedom can be partly reduced. And observe that net elec second kind are included here. This is an example for k equal 1 of the original degrees of freedom, values of the tangential component, two values of the tangential component, which is linear on each edge, plus 3 degrees of freedom inside corresponding to that. And on a polygon like this, with the serendipity procedure, we can eliminate all the 3 degrees of freedom. So we obtain the degrees of freedom will be just those one, exactly what we have in net elec second kind, which are included here. And if the polygon is a triangle, then we have exactly just net elec second kind of degree 1. And so for the other degrees, when possible. Then we have node. The space of node will be of degree k plus 1, will be made of functions which are polynomials of degree k plus 1 on each edge, and Laplace of degree k. These will be the degrees of freedom. And again, here too, with the serendipity version, the internal degrees of freedom can be reduced. Maybe not always eliminated, but sensitivity reduced. Polynomials of degree k plus 1 are included. And here are the degrees of freedom. For example, for the case k equal 1, we have polynomials of degree 2 on each edge, plus the moments, say, against P1, so 3 inside. And with the serendipity procedure, we can eliminate all the internal degrees of freedom and reduce to everything to polynomials of degree 2. Now, the local spaces on the polyhedra, we have an edge space, which is made of vectors which have the tangential component on each face belonging to the edge space, as before. V dot t continues on the edges, divergence of degree k minus 1, curl pk, similar to what we had before. The nodal space will be made of functions which belong to v node k plus 1 on each face, and the Laplace is of the inside is of degree k minus 1. And then v face, normal component of degree k minus 1 on each face, curl of degree k, and divergence of degree k minus 1. Don't read that. These are just the internal degrees of freedom for the edge. This is a definition of the edge scalar product. You see that it's very similar to what we had before. L2 scalar product of projection onto constant plus a stability term. This is the stability condition, and this is the consistency which is verified. For the nodal space, these will be the internal degrees of freedom, and these degrees of freedom allow to compute the L2 projection from vk plus 1 onto polynomials of degree k minus 1. Finally, these are the degrees of freedom for the phase space on the polyhedra, and from them we can compute the projection onto polynomials of degree up to k plus 1. And the scalar product in the phase is associated to this norm here. The global space are built gluing together the local spaces, and we proved that this sequence is exact. And then we define an edge scalar product, a phase scalar product exactly as before. And if we do that, then we can prove that this form of the discrete problem has a unique solution with p identically 0, and the error is bounded by these three terms. Here we have a first term, which is the error between h and the edge interpolant of h. The second term is the error between, again, h and the projection of h onto polynomials of degree k. And the third one is the error between the permittivity h minus the projection of B. This is the B part, the magnetic induction. So we will have order h, provided that all the three pieces are order h. Moreover, the curl of h is equal to j by definition, and curl hh is equal to jh. So the error on the curl part is the interpolation error on the current. Very quickly, a numerical test. Here we are on a cube, and we have four types of meshes into cubes, more distorted, till the random one. And here, the first problem is with constant permeability mu, and the exact solution, this vector here, and the error that will be plotted is this error here, as before, between h and the projection of the discrete solution onto constant, because we don't know the discrete solution inside. And this, if you can read it, if you can see it, sorry. Here we have the slope for the first problem. Different color for different meshes. In blue, the cube, in green, the 9, the CVT, and the random. And there is a comparison between the original version and the serendipity version, the one with less degrees of freedom, and you see that the curve superimposed. This is for the degree 1, and the same happens for the degree 2. This is the L2 error, so we expect order 2 in this case and order 1 in this case. And then the second problem is again on the cube, this time with a variable permeability. This is the exact solution that we took, and again we compute this error here. And those are the convergence curve for degree 1 and degree 2 for the original and the serendipity version. And again, also on this example, on this test, we have the expected slope in both cases. To conclude, I presented the lowest order element for magnetostatic problems, which is the extension to polyhedra of lowest order Nedelec first kind. And the element proved robust, very robust to distortion. You saw, I showed mesh very, very distorted, but the element doesn't bother. And then, very quickly, just to let you know that it exists, I present a family of elements which are the extension to polytopic decomposition of the Nedelec second kind in 3 dimensions. I thank you for your attention.